Hi, I'm Brian Mullin, and this is Balls Out Physics, Episode 3, Centripetal Force, Gravity, and the Sun. Now before you watch this episode, if you haven't watched Episode 2, please go back and watch that, because this episode is really a continuation of that episode, where we talked about the bread and butter physics equation, F equals ma, and the equation for gravity, over here, Fg equals the gravitational constant, which the episode was titled, times one mass times another mass divided by the distance between them squared. Now in that episode I focused on the fact that the gravitational constant may have been calculated by estimating Earth instead of through experimentation, as we've been told. There's really not a whole lot of evidence showing that these experiments have worked. We're told that they worked. We're showed, there's articles out there showing pictures of modern day torsion balance experiments that say that they work, but a lot of people out there say they don't work. And I've never seen any replica of the original torsion balance experiment that Cavendish did, or Henry Cavendish did in 1798, which I'd really like to see, because that's really where it all started. But anyway, even if they did determine this constant through experimentation, it doesn't really matter, because of what I'm about to cover, in my opinion at least. So, diving in, this episode is really about the relationship between centripetal force and gravity, or setting them equal to each other, because the gravitational force that's supposed to hold our Earth to the Sun and make it orbit the Sun is really a centripetal force, and this is the theory. Okay, so what a centripetal force really is a force directed towards the center of a circle. So a ball on a string is the best way to give an example of this. You have a ball or a mass, a little foam spherical Earth here, and a string representing the force pulling it towards the center, which in this case would be my hand, where you could say that was the Sun. So you spin this around. Okay, the tension in the string is the force. Okay, and that creates a velocity. The ball resists that force by traveling in a circle around the center point, or the Sun in the case of the solar system model. Okay. So I have written down the equation for centripetal force over here. It says centripetal force is equal to the mass, or the ball, times the velocity squared divided by the radius. So the velocity would be the speed that it's traveling at around the circle. The radius would be the length of the string in this case. Or if you look at the solar system model, which I've got drawn right here, with just the Earth and the Sun, it would be the velocity, the instantaneous velocity of the Earth at any point around the circle, and the radius would be the distance from the Sun, and the mass, of course, would be the mass of Earth. Alright, so it is the mass of Earth, not the mass of the Sun. Remember that. So this equation is really derived from F equals ma. Like I said, this is the bread and butter equation of physics. The only difference here is we're dealing with angular acceleration, or centripetal acceleration, whereas in the last episode we were talking about the acceleration towards Earth, or acceleration due to gravity, as it's called. Okay. So just to show how this works, acceleration, angular acceleration, or centripetal acceleration, call it AR, it's commonly called, is equal to v squared over r. And let's say, just for a quick example, that when I'm spinning this, it's traveling at 1 meter per second, and let's say that the length of this string is 1/10 of a meter, just to keep it easy, which is 0.01 or 0.1 meters. So 1 meter per second over 0.1 meters. And this is 1 meter per second squared, actually, up top, velocity squared, gives us 10 meters per second squared, which is pretty close to the acceleration due to gravity, or the acceleration at which things fall towards Earth, which is 9.81 meters per second squared. So the units are actually the same. Okay. However, in this case, the acceleration is considered to be acting towards the center of the circle, or towards where the tension in the string is for the spinning ball. Yeah. And if you remember in episode 2, I said that acceleration is any change of velocity. So since velocity has both a rate, as in miles per hour, kilometers per hour, meters per second, and a direction, if the rate remains constant but the direction changes, it is said to be constantly accelerating. So, theory is, since this Earth would be traveling around the circle, or it's actually, NASA tells us it's elliptical, but they also use this equation, which is based on a circle, this velocity is constantly changing as it travels around the sun. Okay, the velocity, the direction of the velocity over here would be pointing down to the right. Okay, it's pretty simple. So, Cavendish came up with this value of big G, and then they calculated the mass of Earth, as you saw in the last episode. And then they could move on to the sun. They were basically assigning numbers to the solar system model that Copernicus had come up with a few hundred years before. Okay, so as I've written here, I have centripetal force between the Earth and the Sun, or the force pulling the Earth towards the Sun, is equal to the force of gravity. So what you can do is say these equations are equal. You can actually set Fc equal to Fg. So let's just say Fc up here equals Fg. Okay? But this is really m squared, or m, excuse me, times v squared, getting a little ahead of myself there, over r is equal to big G, the gravitational constant, times the little m, which is the mass of Earth, times big M, which we're going to say is the mass of the Sun in this case, over r squared. Okay? Now, at the time, they were pretty sure they knew how far away the Earth was from the Sun. They used sextants and other devices to get a measurement. Now, of course, the way a sextant works, as I've looked into, the Sun can either be a few thousand miles away and 32, 33 miles in diameter, or it can be 93 million miles away and have a diameter that's 100 times the Earth. It's either or, based on how a sextant works. I haven't used one yet. I'd really like to. Nobody uses them anymore. It's an old-fashioned tool, but it'd be really interesting. But anyway, let's assume that they were right, and the actual distance in meters is, or in kilometers, is 149.6 times 10 to the 6 kilometers, according to NASA's fact sheet. And so the mass of Earth, just like the mass of the man in episode 2, cancels out. Kind of funny how this gravity equation kills the smaller mass. Anyway, it's nature, right? That's what we're told. So now you have the mass of the Sun, you've got the velocity of the Earth, which you know because you know the radius of Earth, and you can calculate the circumference of the circle, or the distance it travels around the Sun, which circumference, I'll write that over here, is equal to 2 pi r. Okay? So they already knew the distance, so they can figure out the velocity, because velocity is really distance over time. So what they can do is say that velocity is equal to 2 pi r, and we'll call over big T. In physics, big T is usually considered a period, or the time it takes to make one revolution, which in this case they thought was 1 year, because the Sun does its thing in 1 year. 4 seasons it takes, though they tell us 365 and a quarter days, which actually comes out to 31,557,600 seconds, which is what you would have to do to make all these units work. But I'm not going to go through all the numbers. I'm just going to show the algebra to show how this was done. And you can look this up. This is all over the internet. So we need to isolate the mass of the Sun. We have everything else. We have the velocity, which can be calculated with this equation. We have the radius. Radius is the same over here, and they had the gravitational constant, which who knows how that was really determined, but it doesn't matter. Okay, so showing some simple algebra here, you could say multiply this side times r squared over g, multiply this side times the same thing, r squared over g, just to show the steps. So R squared cancels, G cancels, G cancels. Over here you've got R squared times V squared over G times R. And then this R cancels. So you really just have R times V squared over G is equal to the mass of the sun. And that comes out to 1,988,500 times 10 to the 24th kilograms. Now this is many, many times more massive than the Earth. The Earth is actually 5.97 times 10 to the 24th kilograms, I think. Is that written down? Yep, roughly. So, many, many times more massive than the Earth, is what we're told. Which, you know, see the solar system model, the sun appears huge compared to all the planets. So, with this relationship now, they calculated the mass of the sun. But as you saw in the example, the mass of the Earth that's orbiting the sun cancels. So, well, the first time I did this, I kind of got a little excited at first, but then I realized, well, the mass of whatever's orbiting the sun just cancels out. It doesn't matter. And so I said, well, what can we do now? You know, because I thought for a minute I'd get to go calculate the mass of Jupiter and Mars. For some reason, I've always liked Jupiter, and that was my first thought. And I said, well, no, you can't, because the mass cancels out, as I showed. So let's go back. Get that equation back up here. What you can do, what people have realized though, is since V is actually equal to 2 pi r over the period, you can say V squared is equal to 4 pi squared times r squared over t, over the period squared. See, it's just this times itself squared. Okay, so going back to that original equation, we can write the centripetal force equation now, with that original relationship, that is. We can substitute this for V squared, and that'll give you that'll give you 4 pi squared times r squared over r, because r was still on the bottom, and this t squared comes down here, over r times the period squared. This r cancels and that r cancels, so you get 4 pi squared r over the period squared, or big T squared. Okay, and then set that equal to big G times little m times big M, mass of the sun, divided by r squared. Okay, now mass cancels again. But what you can do now, since you know the mass of the sun, or what they say you can do now, is determine the distance of anything orbiting the sun if you know the amount of time it takes, or the orbital period of that object, right? This is what's currently done. So what this breaks down to is you need to get r by itself, because r is the distance, right? Once you get r, you can determine the velocity as well, according to the theory. So to get r by itself, we multiply this side times r squared. Let's do r squared over 1. And this side times r squared over 1. That gives us 4 pi squared r cubed equals, cancels on this side, g times big M. And then we want to get r by itself over here, so we just divide by r pi, or by 4 pi squared. I'm not going to actually show the steps, but we'll just say r cubed equals g m, nope, I missed t cubed. And let me just write this out. What this actually works out to, instead of doing all the algebra for you guys, I can do it, I've already done it. And if you look this up, this is the period equation. R ends up being, so I'm not boring you with all the algebraic steps, the cube root of the gravitational constant times the mass of the sun times the period squared over 4 pi squared. Okay, that's what this breaks down to. You can solve for r. And so what they say is that if you know the period, like for instance, Jupiter takes 11.86 years to do its thing. You know, we see it, if you pick a point in the sky and you record where it is in the sky, it will take 11.86 years to get back to that point. People have been watching these things, the wandering stars, as the ancients used to call them, or the planets, 8 of them, that, well, 7 we can see, we're supposed to be on one of them, since the beginning of time, as far as we know. So this is well documented. The period, or the time it takes for each one of these 7 entities to do its thing, is well documented. Okay, and so you would need to convert the time for Jupiter into seconds, and that is actually, just to throw a number out there, 374,198,400 seconds. It's a pretty long time. Lots of seconds. So you plug that in, you've got how far Jupiter is from Earth, right? Well, I don't really agree with this. And the reason I don't is because we got to back up here. The only thing that matters, according to this equation, is the mass of the Sun. The mass of Jupiter doesn't matter, so Jupiter could be a golf ball, or it could be, what they tell us, something with a mass of 318 Earths, roughly. So, based on this, the mass doesn't matter. What about this over here? This original proportion that I talked about in episode 2. As the mass of each object increases, the force of gravity increases. As the mass of one of those objects decreases, the force of gravity decreases. But the way I look at this, it's saying that the Sun controls only. Let's back up a little bit. Maybe I'm getting a little ahead of myself here. Go back to this original relationship. We don't need to do this anymore. We'll go back to just keeping it simple. You say the centripetal force Fc. You say the centripetal force Fc is equal to the mass of the object orbiting the Sun, which we still have as the Earth here, or Jupiter, or Mars, or whatever you want it to be, times the velocity of that planet or wandering star, divided by the distance from the Sun, r, is equal to the gravitational constant times the little m, which is the mass of Jupiter or Mars or Earth or whatever, times big M, which is the mass of the Sun. I'll write M Sun here to clarify that, times the distance that object is from the Sun squared, and that's equal to the force of gravity. These are said to be equal, and this is how the solar system was built, or that's how we applied numbers, or they applied numbers to our solar system. Okay. Well, this math is canceled. So now, if you just cover this side and look over here, this is no longer a force. You need this mass to have a force, right? Just like you need a force down here. Or if you cover this side, this is no longer a force because the gravitational constant needs the units of mass, in this case kilograms squared. So this is no longer a force. So if you cancel out these little masses, you cancel out the force. You can't have your cake and eat it too, so to say. This defies logic, in my opinion. How can you say that the mass of the object orbiting the Sun does not matter? It does, because that's what creates the force. This says that the force goes away, so then what happens? This doesn't make sense. But if you go back to that equation that I showed, you say R equals the cube root of G, which you can solve from this, just to show this again, times the mass of the Sun, times the period of the object orbiting the Sun, how long it takes to go around one time, divided by 4 pi squared. If you take the period of any of the planets, I did all the planets, even Earth, or the wandering stars, and you plug this time in, you get the exact radius, roughly the exact radius that NASA has on their fact sheet from every one of the planets, their fact sheet. So, you know, I've looked into this for a while and I've been aware of how masses are calculated. So you say, how do you figure out the mass of the object that's orbiting the sun then? Because this says that the sun wins. The mass doesn't matter. I don't know. Well, what they say is they observe the object. They observe Jupiter, for example, and they observe the moons that they tell us are orbiting Jupiter. And they can tell by the tug and the pull back and forth, say like, I don't know, let's say that this is Jupiter and this is a moon, and they can see the little wobble it gets from the moon going around it, the wobble effect on the planet, that they can estimate the mass. Okay, and maybe they compare it to what they think is the relationship between the sun and the earth. But it's all from observation. It's kind of guessing, I think. Lots of guessing. When I took astronomy, I was kind of blown away by this, especially because NASA tells us that these are facts. But it doesn't matter if their estimation's wrong according to this equation, because mass doesn't matter, right? But it does matter. This equation right here, this gravity equation, causes these two forces to cancel out. Just like in episode 2, when you set this equation equal to the weight equation, the smaller mass is eliminated. This is... how have we gotten this far? Is what I'm asking. I mean, this is my opinion, but I don't understand how the smaller mass cannot matter. And both equations depend on that smaller mass. Just because the mathematics works doesn't mean it's logical. This is a huge mistake that I think we've been making for years. If somebody writes an equation and the math works, things cancel out and you get a number, and we think we've actually figured something out, but you always have to employ logic. Actually, Tesla had a lot to say about this, and if you know anything about Tesla, I think he was the greatest engineer that ever lived, but that's why we have alternating current, and it's kind of strange that we don't really hear much about him in our history books. Anyway, so I started thinking about this, and well, I started really thinking about this equation and how it came about, and how it makes this guy over here win. Sun wins. Sun controls. And I started thinking about who came up with the solar system model. And that was a man named Copernicus. You can look this up. Copernicus was the first person to propose the solar system model. And well, Copernicus was a pagan. Pagans worship the sun. Interesting. Copernicus proposed the solar system model to the Church of England in the early 1500s, maybe 1513, 1514, somewhere around there. I might be wrong on that, but early 1500s. He proposes this model to the Church of England. You can look all of this up. And Church of England says, yeah, that sounds great. We're just gonna get rid of 1500 years of Christian belief or Catholic belief, I guess, if you want to call it that, and we're just going to adopt this model. Because the Bible actually says the earth is flat and it doesn't rotate, and it says that everything goes around us. Now, some Christians have argued that, but my Bible, I was raised Catholic. I don't really consider myself anything. I consider myself my own religion, the 1 in 7 billion religion. It's a separate issue. But turn to page 5 in Genesis, and we've got this. New American Bible, Catholic Bible. What's that? That shows a flat earth with a firmament and the stars and the sun and the moon going around us. That's strange. And they would just give it up because a pagan came and told them that everything goes around the sun? People hammer science and say that science is the answer. They don't realize that the science of their world and this solar system that we're supposed to live in actually came about through religion. Very strange to me. I'm really starting to doubt things. What's actually funny is in November of last year, I was joking, around November of last year, I was joking with my roommate about the Bible and saying, I don't really believe this, because I opened this page and said, look at this flat earth thing. I mean, this is ridiculous. I was drinking beers with him, we were laughing about it. I mean, talk about putting your foot in your mouth. So, something to really think about. You know, the Freemasons came along, obviously, or not obviously, but I said in the last episode that Newton was a Freemason and so was Henry Cavendish. And if you study Freemasonry at all, you'll find that they have a lot of sun symbolism. They really seem to like the sun. Is that a coincidence? I don't know. You know, I'm asking questions here, like I said. If I'm proven wrong, great, you know, I can go back to living a normal life, I guess. What we thought was a normal life. But think about this relationship and how this equation, in my opinion, seems to be designed to do exactly what they wanted. A solar system. To make us revolve around the sun, or to make us worship the sun. Are we worshiping the sun through science and we don't even realize it? You should look into some of these organizations, some of these secret societies that seem to be prevalent throughout politics, science, or even religion. The Vatican has a lot of sun symbols too, which I find very strange. Why did they give up what the Bible said in 1500? Something else to really think about. You know, since I started studying this, I've started watching the sun. Now, I don't recommend looking directly at the sun because you'll see spots for a little while. But if you notice, the sun comes up in the east, comes up above the horizon in the east, and as it moves through the sky in the day, it starts off, the diameter appears to be a little bigger than it does at midday. And it's very noticeable when you look at the moon this way. The moon does the same thing. The sun and the moon move through our sky at the same way, really. I mean, of course, the sun is moving faster than the moon. It seems like, you know, the moon has a different period compared to the sun, but they both do the same thing. You would think if one's going around us and we're going around the other, and the other moves through our sky because we're spinning around our axis, you know, if we live on a ball Earth, you know, if this is our axis and we're spinning and this is what makes the sun move through our sky, that they wouldn't do the exact same thing. Actually, I think it would be very clear to us that we are rotating relative to the sun and that we are moving around it. But they both do the same thing. Think about that. How is that possible? I think they're both going around us. How can they not be? I don't know. Maybe I can be proven wrong on that. But if you want to look at the sun, I highly recommend getting a welding mask. It's really cool to look at the sun through one of these because it looks green and you can actually see that it's about the same diameter as the moon. It looks identical to the moon when you look through it through one of these. So, asking questions again, but pay attention to the sun and watch the moon and ask yourself, what do you think? Are we going around the sun, or is it going around us, just like the moon? I don't know. But I'm going to keep watching it, because it's interesting. And I really want to know what my world is. We all need to work together and figure this out. So until next time, we'll be talking about a thermosphere, and maybe something else in episode 4. See you then. Peace.